Hi everyone, thank you for joining us to launch the Modular Gold Cup probe today. My name is James Cross. I am the marketing director here at Land. I'm joined by my colleague Jason Rushton, who is an application engineer. Really exciting product. We did the internal launch for this last week and had a ton of questions and a load of excitement around the product internally and with our partners. So it's great to present this to the external audience as well. I'll just take control of the screen. So we are doing a quick introduction of the technology, the suite of products that we have, the type of furnaces that we've got some experience on, and then a little bit of background into TMTs and Land's history in the Gold Cup probe. So to kick us off, the Gold Cup is just one of four main products that we have in this suite suited to tube metal temperatures. The Cyclops is our core pyrometer. We've supplied over 10,000 of these to industry since that was first introduced to the market in the 1970s. The Spot pyrometer we launched a few months ago now and is used on fired heaters across the industry. The Gold Cup reference pyrometer we're talking about today is really our quite niche, quite mythical in the industry reference pyrometer. So this is how we determine true tube temperatures. And then obviously our fixed and portable thermal imager range. So these all work together to create a kind of nice portfolio of portable, fixed pyrometry and thermal imaging products that we use every day in the field. So our experience industrially in the petrochemical and refining sector is really in the refining, biorefining, gas to liquids plants. There's a huge range of furnaces you can use this equipment, all four of those products, but especially the Gold Cup pyrometer on. More so than the other industries, ethylene, methanol, and ammonia, you're really probably only going to use a Gold Cup on a steam methane reformer or an ethylene cracker. That might be a naphtha cracker or an ethane cracker. Whereas in the refining sector, you might be using this on a crude furnace, on a platformer, on a hydrogen unit. So a huge variety of furnaces. Really what we're talking about today is applications on high temperature furnaces where that critical temperature information and the accuracy of that is really important. So as you'll all know, I'm sure, TMT stands for tube metal temperature. I was based in the Middle East for 5 years and people often called it tube wall temperature, TWT. And it's the outside surface temperature of the process tubes in these refinery units or crackers or steam methane reformers. The other information you might get from those units is the tube inlet temperatures, the outlet temperatures. You might see that as coil outlet temperature, and of course, flue gas temperatures. But tube metal temperatures are a critical variable that are only really currently measured either with a small number of fixed thermocouples or a number of portable pyrometers that are periodically used to take TMTs around the furnace. And controlling those TMTs is important for different reasons on different heaters, but there's normally an optimal window where you're balancing the production yield and the reliability of the tubes and the furnace. Of course, in the case of ethylene on crackers, you're also mitigating coke production as you go through a run. And if you are too hot, you'll get coke formation or a rapid tube failure. And if you're too cold, then you'll be running inefficiently. You'll have high methane slip in the case of steam methane reformers or a low yield. And there's, at least we're told by the catalyst suppliers who have to supply catalyst on a very quick turnaround, at least one major steam methane incident every year, steam methane reformer incident every year. So optimization is critical. So we introduced this Gold Cup pyrometer to help our customers use the pyrometer and use the thermal imager with a higher level of accuracy. So accuracy is the key word here. Usability at the time we invented it and practicality was a second and third concern. So what you've found over the years, and we've produced different models of these, it has a good status in the industry. The IRTC does recommend the Land Gold Cup for true tube temperatures. There's a lot of academic studies, including in Peter Saunders' thermometry user guide, that point to the benefits of the Gold Cup, but we didn't really focus on the core usability and practicality, and that was the challenge given to Jason in his development of a new Gold Cup. So I'll hand you over to Jason to talk you through what we've done with this new development, and then we'll come back to Q&A at the end. So please type your questions away in the questions and answer session tab at the top of the window, and we'll take those at the end. Okay, over to you, Jason.
Thank you, James. Hello, everyone. I think the first thing we need to do is really understand why using a Gold Cup is valuable. Why can't we just use a Cyclops or a thermal imager? And that really comes down to the fact that every IR measurement is affected by three things: emissivity, background radiation, and transmittance. So emissivity, what is emissivity? Emissivity is a dimensionless value between 0 and 1, 1 being a black body, a calibration furnace, it's the best way of thinking about it is it's a ratio of how much from when we take an IR measurement, how much of the energy the camera or Cyclops is receiving is from the target, and how much of it is a reflection from the background. In the industries we're talking about today, the background is always hotter than the target than the tube, so we always need to consider emissivity and background, which are linked together. And that background radiation is important. Another an important part of the picture. We need to know what the temperature is of the background. With a Cyclops, that could be taking separate points on the wall. With a thermal imager, picking up some of the wall temperature and then doing that calculation to work out what true tube temperature is. The third thing we need to consider is transmittance. So we need to pick a wavelength that is that we can see through the atmosphere to the target with minimal or no energy loss. In the kind of furnaces we're talking about today, that's 1 micron, 1.6 micron, and 3.9 micron are the widely accepted wavelengths. So if we look at that now, so how does a Gold Cup work? So a Gold Cup is unaffected by all three of them properties that we've talked about: emissivity, background, and transmittance. It's unaffected by background radiation because as it touches onto a target, whether that be a flat plate or a tube, it forms a seal with the target, and means that no background radiation can get into the measurement. The second point is that because gold is a very good reflector, so the inside of this hemisphere is gold coated and has a high reflectivity, the energy from the target is reflected back and forth at least 12 times before it can reach the fiber optic light guide. Every time we reflect infrared radiation, we have an emissivity enhancing effect. So as you can see, number of reflections along the bottom and emissivity along the side. As we increase reflection, we increase emissivity. And this hemisphere is designed so that we have at least a minimum of 12 reflections before the energy can reach the fiber optic. And at 12 reflections, the assumed emissivity is 1. So we have an emissivity of 1. We have no interference from background, and the wavelength of the thermometer is 1.6 micron. So we have solved all three of them issues, which means we can get true tube temperature. And this is really the only way to non-destructively get true tube temperature in a furnace. So that's been really the same for and the physics has stayed the same for all of our Gold Cups to date. So what's kind of changed with the new Modular Gold Cup, and really it's been a learning curve for us in usability, adaptability, and really trying to make the user experience much better for the customer. The Gold Cup, as James touched on, is well received in the industry and well recognized. But it is also in most cases a 3 meter long probe, which is very difficult to operate, and in some cases, depending on the type of furnace we're using it on, that 3 meter length can cause issues when we've got very small walkways. We've got a lot of ancillary equipment on the side of the furnace. It means it's sometimes very difficult to actually take measurements in the furnace because we've got this big probe. So the modular, as the name suggests, allows us to make different shapes of probe, different lengths of probe, to suit the application we're looking at. And really, it's been designed with industry, with experts, and we've gone through a real iterative process of design, with people in the industry following site trials, to iron out all of the issues that we could. The two main issues was the probe is 3 meters long. It's very expensive and very difficult to ship around the world. This Modular Gold Cup packs down into a much smaller footprint, and can be shipped much easier, under 32 kilos for the heaviest kit. It's also can be taken on most commercial airlines as excess baggage. The second issue was, well, we want to use the Gold Cup on different heaters, and in the case of smaller refinery heaters, we want to be able to take the backside of the tube, the hot side of the tube from a peep door. So that's where this kind of 180-degree bend shepherd hook style probe configuration is really targeting. And finally, not all customers have water available. All of our Gold Cups up to now have been water cooled. This probe is air cooled. It's much more available on site. The air exhausts into the furnace, so we haven't got multiple lines coming back out of the furnace, and so obviously we haven't got the weight of the water. So there's a couple of different models, and I've included the water cooled here. So that's our current offering. We'll still be offering that to the customers that want it. Some customers that is the preferred solution. That's the solution that works best for them. Primarily going to be ethylene crackers, steam methane reformers, water cooled, 3 meters long as standard, with no adaptability, one welded assembly, and then we've got two kits for the modular Gold Cup. So the first one, the straight kit, as the name suggests, only has the straight sections, targeting again ethylene and steam methane reformers primarily. The modularity means different lengths can be made, and ensures the right length for the target you're trying to take a measurement of, with a max length of 3 meters. So that's good for single sites with restricted access on the walkways that need to be conscientious of probe length. Also survey companies, corporate teams, people that are going between sites. The modularity really adds value there. The second kit is the 9180. So still very applicable to SMRs and crackers, but also with the 90 degree and the 180 degree head, can be used on kind of smaller can style refinery heaters, crude heaters, cokers, that sort of thing. The trade-off there is that the max length is in a straight configuration is 1.8 meters. So that's really targeting the refineries. Again, could be survey companies, and I want to stress, absolutely still can be used on ethylene, on SMRs. It's just that the max straight length is obviously that bit smaller, bit shorter. Sorry. So what's in the kit? In the straight kit, we've got a multitude of different straight lengths. So 300 mil section there, and then multiple 600 mil sections. Again, another thing we found out following site trials, to build this on the floor in a refinery or a petrochem unit, is a little difficult. So we've included some assembly stands, just X style slot together stands that we can prop the probe up, so we can get really easy to makes it really easy to bolt the flanges together without getting any bolts cross-threaded. For the obviously this product's going to be sold globally. We have inlet fittings for the 2 air connections will be available in BSP and MPT. So BSP will be directly connected to the male quick release plug, and we will provide in BSP to MPT adapters. So customer connections are either 1/2 inch BSP male, or 1/2 inch MPT male. In the 9180 kit, as the name suggests, we've got slightly less straight sections, but really the main difference is the part 5 and part 7 here. The 90 degree head and the 180 degree head. So that's the primary difference. Still having the assembly stands, still has the 2 options for fittings. Key features. So I think some of these are really intuitive and really clever. The flanges, as anyone that's used our current Gold Cup knows, one of the most common ways is to rest it on the bottom of the peep door. So if we had normal traditional style flanges, we'd have to slide the probe down a section and lift it over the flange at every joint, which we didn't think was very usable. So we've designed flanges with chamfers on either side and recessed fixings to allow us to still slide the probe along the bottom of the peep door and then do the same when we're retracting it. So that I think that's been a really good development. The cooling holes and the fixing holes are pokey oak, which means they are pokey oak means mistake proofing. In our sense, it means that we cannot secure the sections together in a way that means we couldn't get cooling air through the probe. That whatever orientation you mount the sections together, you will always get cooling air going through the holes. And I mentioned earlier two air connections. So we have that again has come from industry feedback and trials. We have the continuous cooling air. So that's as it would suggest, air that is on all the time whenever we're using the probe. And that air is ejected into the furnace away from the head. So this is the head module. So this is the gold hemisphere that will touch the tube, and the air is ejected through holes that you can't see, but roughly where my pointer is there, back away from the tube we're trying to measure. And then because air is not as good a coolant as water, we felt the need that we would have to improve the cooling down time between measurements. So that's where the out of process cooling comes in. So when the probe's on the walkway, you can connect a second airline, which blows air directly down the central bore of the sections and directly over the thermometer module to cool the system down in between measurements much more quickly. And that air is ejected between this black flange and the head module, but cannot be used in operation when the probe's taking a tube temperature. But all the fittings for both the continuous and out of process cooling are quick release swivel self-sealing fittings. So with the out of process, where you're going to be connecting and disconnecting regularly, you can keep the line pressurized and connect and disconnect as you will, as they're self-sealing. So you're not having to go back to a regulator all the time. And finally, the final innovation we've included in this product is that the black flange here is designed to reduce the amount of incident radiation getting into the measurement. So with some of the more difficult geometries that you could build with especially the 9180 kit, we want to make sure that we don't get any incident radiation into the measurement, and the black flange is there to help reduce the likelihood of that. We have the web page has gone live. If you go on our web page and look under portable infrared thermometers, you'll see the Modular Gold Cup section. the brochures on there, user guides available on there, couple of short videos on how to fit a shroud and how to remove the gold cup for cleaning. And yeah, so they're all available on there. I'd encourage everyone to go have a look into the documentation, and then any questions anyone has, obviously feel free to reach out to your regional representative. So conclusions from me, the product is a unique product. It's been designed with people in the refinery and petrochem world to solve some pretty difficult challenges. There's a really good return on investment from this, because if you can take true tube temperature, you obviously can potentially run your applications hotter, where previously you couldn't. As with any reference pyrometer, it's important that we have traceable calibration. So standard calibration, same as all our products as available, it will be part of the package as standard. And there is options for UCAS calibration, either periodically or as part of an AMI care contract. And finally, the final thing I really want to stress to everyone, straight modular is primarily targeting ethylene, steam methane reforming, them traditional Gold Cup markets. The 9180 modular is more focused on the smaller refinery heaters with poor access, but can still be used across a full range of furnaces. And for those customers that still want to carry on using the water cooled, that is still going to be available for the foreseeable future. So with that, I'll hand back over to James to have the last couple of words before we go on to questions.
Yeah, thank you, Jason. Great job. And just quickly, it's obviously great to have engineers in our company that will listen to the market, develop a product that's pretty innovative. Not a lot of pyrometry products on the market that have got such complex cooling arrangements. So really proud to have you on the team. We do have some nice challenging questions as we like. So I'll start this off with Thomas's question on the shroud arrangement or the standard Gold Cup arrangement. So how does the Gold Cup shadow, or how much does the Gold Cup shadow the measuring point area and influence the temperature reading by cooling? So Jason, what are your thoughts on that?
The Gold Cup does shadow a tube, and obviously having a contact with a tube is something that will, obviously the probe is much cooler than the process tube, so that will have an impact. It is a real world measurement. We need to be realistic. We need to try and minimize that contact time. The way I've always done it is, as you make contact with the tube, you take the reading. Normally in a team of 3, you'll have one person on the handheld display continuously taking a reading, and then as you touch on, the person at the front of the probe will say now. They'll release that trigger and freeze the reading, and then obviously you've got the actual temperature. We want the temperature as we touch on, because obviously that is the point where we've got no impact from the probe cooling the target. So hopefully that answers the question.
Yeah, I think so. Actually, Thomas, I think we have your email from obviously joining the webinar. I'll send you a chart that's actually in the Peter Saunders book that I referenced that shows how the temperature of the Gold Cup changes as you approach the tube. So as as you start to form the shadow, yes, the background radiation is now shielded, but the tube itself, the rate at which it cools is relatively slow in the first couple of seconds. You might lose a degree or 2 degrees as you're taking the reading. That's why you need to take the reading as soon as it touches the tube. But yeah, I'll send you that chart. It gives you an interesting idea of how the Gold Cup temperature changes as you actually touch the tube. So some good questions from Marion. Sorry if I've butchered the pronunciation. So the Gold Cup is often used to calibrate normal pyrometer readings. How often would this be required, Jason?
As you've touched on, I'm an engineer. I have a slightly different view. If you ask a survey company, they'd probably say every 6 months. My personal opinion is you should be led by the data. If you take Gold Cup readings regularly, every 3 months, every 6 months, in the to start with, you can analyze that data set and really plot how much that emissivity value, which is what you're trying to derive, is changing over time. Obviously, brand new tubes, the emissivity value will likely change a lot over the first 6 months, and the same at end of life, last 6 months, 1 year, the emissivity value will probably change quite a lot. During that middle period, probably quite a slow change. But yeah, my answer is be led by the data. If you commonly people say 6 months, but I think personally being led by the data is a much more effective way to go.
I think one second asterisk on that would be it depends on how hard you're running a plant. If you're at 100% load and looking to achieve even higher, then you're probably going to need to check and validate your pyrometer readings a little bit more often than if you're running at 70-80%. Likewise, you might be looking at a crude furnace which needs very little monitoring, but every now and then you have a tube which decides to coke up and starts to overheat. You're probably then going to pay that more attention. So it really does depend on the specific conditions of the unit, not even the plant, the specific unit you're talking about. Which is not a simple answer, but it's probably the true answer. And then final question from Marion is, what is the cooling air flow rate and pressure required for the continuous cooling connection?
For the continuous, we would recommend 1,000 standard liters per minute of air. I don't have the pressure. Obviously, that will depend slightly on what orientation you've designed. Obviously, shorter probes have less flanges to go through, so pressure will be slightly less. But certainly not under kind of 8 bar usual refinery petrochem air pressures. Good.
Lots of testing. I think you mentioned, Jason, the unit's been tested on. I mean, the product before we did the formal release tested on 3 or 4 sites, and again, the specific cooling flow you may be able to achieve depends on the flue gas temperatures. So one final question, and then we'll finish the webinar for today. that's just come in. At sites, there are often different cracking furnaces with tubes of a different age and hence emissivity. Operators only use one calibration or emissivity. What would the error be in Celsius?
Very difficult to say. The age does certainly have an effect on the emissivity. I've seen 50, 60, 70 Celsius differences between emissivity 1, so taking a measurement without using a Gold Cup, and the corrected emissivity. What's the difference between one furnace and another? I'd struggle to say. I think it would depend a lot on the metallurgy, a lot on the age of the different tubes.
I think in nowadays as well on crackers, there's a lot of new alloys that have come through, and you may find that even on one site you've got tubes with two or furnaces with 2-3 different alloys with vastly different emissivities, and like the question hints, customer just wants one emissivity, which can be a challenge. So there's probably not a simple answer to that question, but generally speaking, emissivity errors can result in very high temperature errors, which is where the Gold Cup shows its real value. So there is a question for Brad. We'll follow up with you offline, Brad. Appreciate that input. Thank you everybody for attending on a Friday. We really appreciate you taking the time. This will go online if you want to watch it back, and feel free to reach out to us with any questions. Appreciate it, everybody. Have a great weekend.